beams internal effect. The previous article treated the reduction of the distributed force to one or more equivalent concentrated force and the subsequent determination of external reaction acting on the beam. In this article, we introduce internal beam effect, internal effects and apply principle of statics. To calculate the internal shear force, and bending moment as function of location along the beam. Shear, bending, and torsion. Shear, bending, and torsion. In addition to supporting tension on compression, a beam can resist shear, bending, and torsion. These three effects are illustrated in this picture. As shown in the picture, the V force, the force V is called the shear force. The M is called the bending moment. And the couple T is called the torsional moment. These effects represent the vector component of the resultant of the forces acting on transverse section of the beam as shown in the lower part of the figure here. We have a torsion, bending moment, and shear stress in the section of a beam. Consider the shear force V and bending moment M caused by the force applied to the beam in a single plane. The convention for positive values of shear V and bending M shown in the picture here. The convention for positive values of shear V and moment M shown in the picture for each cross-section, cutted cross-section. From the principle of action and reaction, we can see that the direction of V and M are reversed on the two sections. It is frequently impossible to tell without calculation whether the shear and moment at a particular section are positive or negative. For this reason, it is advisable to represent V and M in their positive direction on the free body diagram and let algebraic sign of calculated values indicate the proper direction. As an aid to the physical interpretation of the bending couple M, consider the picture here. Physical interpretation. Physical interpretation. Consider the beam shown here bends by the two equal and opposite positive moments applied at the end, as shown here. This point and this point. The cross section of the beam is treated as H section with a very narrow center web and heavy top and bottom flanges. For this beam, we may neglect the load carried by the small web compared with the carried by the two flanges. The upper flange of the beam clearly is shortened and is under compression, whereas the lower flange is lengthened and is under tension. The resultant of the two forces, one tensile and the other compressive, acting on any section in a couple and has the value of bending moment on the section. If a beam having some other cross-sectional shape were loaded in the same way, the distributed of force over the cross-section would be different, but the resultant would be the same couple.